Welcome to class today. Just to reinforce some things that I put on the video lecture this morning, and that is there will not be a video lecture on Monday that you have to watch, but we will have the in-class portions on Monday for those of you who are here to answer some questions. There's no real set schedule for what I want to do there, just kind of answer some of your last minute questions. The video this morning had a whole bunch of details about the exam and what I'm expecting, and then I'll be sending out an email this weekend about room assignments and any other questions that get brought into this. Trying to do this the best way, trying to do this the COVID-19 way. It's a challenge, but that's what you pay me for, so I think I can do it. I think we can do it together, so we'll work on that. Make sure you have your appendices. You are required to have appendices by Monday, so if you don't have them, let's get on that today, this weekend, and it is very important that we have those printed copy of the appendices. You will not be able to use a digital copy on the exam. Okay, today what I have for us is I have two table lookups, and then I have some problems that I want us to look at. And the first table lookup I have is propane that's 140 degrees Celsius, and its internal energy is 630.2 kilojoules per kilogram, and I want us to find out what is the specific volume. Okay, I'm going to give you 2 minutes to work on that, and then I will bring that to us, and we'll work on it together. Okay, 2 minutes is up. Let's see what we would do in this case. The first thing we always want to try to do is draw a TV diagram. So here's going to be my TV diagram, or a PV diagram. I guess let's try a PV diagram here because we have a nice even temperature. It really doesn't matter. Both things should tell us the same information, but I'm going to draw a PV diagram. And here's my nice even, oops, that's wrong. Nice even pressure goes down like this. Okay, our temperature, sorry, is equal to 140 degrees Celsius. Let me get my brain in thermodynamics mode just to get it there. Okay, so what I want to do is I want to figure out what our limits are for our internal energy. So in the case actually here, I'm drawing a TU diagram. It's the same thing, but I want to figure out where my limits are. What is my internal energy of my saturated liquid? And I want to find out what my internal energy of my saturated vapor is, and I want to see out where my value of 630.2 lies there. So if I go to my document camera, and I'm going to go look at propane, okay, I'm going to look for nice even temperatures, so I need to find my temperature table. Here it is, temperature table. I'm going to look for 140 degrees. Okay, 140 degrees is not on this table. So that's telling me that at 140 degrees, there is no saturated liquid or saturated vapor. We're above that dome. We've gone past our critical point. So we can't do it here. Now that does not necessarily mean that we are a vapor. It often means that we're a vapor, but it doesn't necessarily mean we're a vapor. But now we can't really look here. We're going to have to go and try to find things in another table. So the first place I'll go is I'll pretend like it is a vapor and see what I can find. So I'm going to go to my vapor tables. And as I go to my vapor tables, I'm going to start asking myself, I'm going to start looking for if there's an entry of 140 degrees Celsius here. And I don't see that on the first page, and only on the second page, if I go all the way down and I can barely get it on the screen here, 140 shows up at 8 bars. But the internal energy there is 665. So I have to keep going and think, well, but at 9 bars, it's 663. So it's going to be less than that. So I have to keep going, increasing my pressure. Let's go here to the next page, middle of the page. 14 bars, there's 140. We've gone down now to 658. We're going in the right direction. Here's 656. Okay, let's go to the next page. 140, 648, 646, 140, 643, 637. Oh, here we go. At 35 bars, we've at 140, and there is 630.2. Okay, so there's where we are. We found our value, and now the corresponding specific volume is right there. The specific volume is equal to 0.01728. Okay, so that is our value that we're going to be looking for. So sometimes you're going to have to search through many tables to figure out what's going on. Okay, so that is a technique, a skill that we haven't had. One of them that we haven't practiced yet in class or on the lecture. Now let's say, what if I did this? What if I said the temperature was equal to 140 degrees Celsius? Oh, let me see here. If I just said the temperature, let's say the pressure was equal to 35 bar, but the internal energy was 625 kilojoules per kilogram. Okay, and I want to find out what is the specific volume there. Okay, now if I want to do that, and for those of you at home, sorry, I have to keep moving back and forth here with this projector. I'm looking at 35 bars, 625 kilojoules per kilogram, and I want to find out what the specific volume is. Okay, so here, if I went to 35 bar, so let's now go to my document camera, 35 bar with propane. .35 bar is way down here for propane, 35 bar. I would look at my internal energy and I would say, whoa, look, internal energy is well above here, above my high level, above 486. So that means it's a vapor. Now we actually know it's a vapor because we just were in the table, but I want to prove it to us. Now we know it's a vapor. Okay, so I'm going to go to my 35 bar vapor entry. Okay, and here we go, 35 bar, and I'm going to notice for my specific volumes, my internal energies, I don't have a 625. I have 607 and I have 630. So I'm going to need to interpolate here. Now here's what some students do. They interpolate to find out what the temperature is that corresponds to the value, and then they interpolate again to find out what the specific volume is. That's a way to do it, but that is not the quickest way to do it. You can directly interpolate between internal energy and specific volume, just like you can interpolate between internal energy and temperature. But we always have done temperature in all of our examples, so that's where people tend to go. We don't need to. We can interpolate between these two. So let's see how we would do this. We would say 630.2 minus, sorry, that's wrong. Well, 630.2 minus, I'm going to go up here to 607.0, because that's between those two numbers. And 630 corresponds to 0.01728, and 607 corresponds to 0.01631. That's going to equal 625 minus 607.0, all over my unknown specific volume minus 0.01631. Again, this is not the only way to do the interpolation. This is one of many ways to do the interpolation, but that is what I used to do this. So let me type this in here. 728 minus 0.01631. And then I'm going to add, I get that my answer for my specific volume is 0.01706 and some decimals there, and that's going to be meters cubed per kilogram. And I have to make sure that that makes sense. The first thing I have to check is it between those two numbers? And it is between those two numbers, so that's good. It should be closer to the 630 value than it is to the 607 value. And it is, so that's good. And even though I may have made a calculation error, at least now I know, hey, I'm in the right range. And so I'm comfortable with that. So as we get more comfortable with these tables, we're going to be able to just run through them pretty quickly. And I didn't take, those of you at home, I didn't take back to my laptop there. You're going to get more comfortable with this. It's just going to take practice. And the good thing, or the unfortunate thing, is that's all you're going to get is practice for the rest of the semester. We're going to have property after property after property that we have to find. On the exam, you're going to have 4 or 5 or maybe 6 property finds. You're going to have to draw TV and PV diagrams, and you're going to have to do some simple interpolation. You know how to use quality and things like that. If you need to work on that this weekend and make sure you're comfortable, because that's guaranteed on that exam, guaranteed. And if you're having trouble Sunday, write me a message, send me a text. Let's get some things figured out. There's lots of resources I put on the web for you, but we need to figure this out. Are there any questions about this that I talked about this morning? This afternoon, actually. Okay. Here's what I'm going to do. I'm going to give you a Fundamentals of Engineering exam problem. This is an FE problem. It's a very typical problem in FE, because FE problems have some dink and dunks. You can just look at it and you know, oh, here's the answer. And there's others that require you to do a little bit of calculation. So this FE problem says you have a closed, rigid tank. It has water in it, and it's at 150 degrees Celsius. And it says if 40% of the tank is liquid water by volume, and 60% is water vapor by volume. The question that they want to ask you here is, what is the quality? What is the quality? Who has an answer right now? Anybody have a value they want to share? I put this on exams in the past, and the most common answer is, well, quality is the amount of vapor in a system, so the quality is 60% or 0.6. That will be the answer, 0.6. Box it, turn it in. And I have put like 10 points on this. So that's a clue, first of all. If I put 10 points on something and you just think it's just written in the problem statement, that there's probably something more to it. And the something more to it here is that quality is not defined by volume, quality is defined by mass. So even though I gave you what it is by volume, that's not the quality. We need to figure out how much mass, the ratio of masses we have here. So we're going to go through this problem. We're going to define what quality is. Quality, X, is equal to the mass of the vapor all over the total mass. Now, we don't have masses, so we have to find something that connects mass with volume. Okay, and so we know that specific volume is the overall volume over the mass. That's what we know. So we know mass is equal to volume over specific volume. So we can take this idea of what mass is, and now we can go back into our quality equation and replace masses with volumes. Okay, so here we go. X is equal to, well, mg is going to be equal to the volume of the vapor all over the specific volume of the vapor. Mass of the liquid is going to be volume of the liquid over specific volume of the liquid. And mass of the vapor is going to be, again, volume of the vapor over specific volume of the vapor. We haven't done anything except for expand what these things are here. Now, we can work from this equation and be able to find out what we need to find, but there's a simpler version of this equation that I'm going to algebraically create. But again, you could solve from here what quality is. What I'm going to do is I'm going to take the top times Vg over Vg. I'm going to take it over specific volume over actual volume. And since I take the top times it, I have to take the bottom times it. Algebraically, it's taking it times 1. And this is going to simplify our life a little bit. And the top is going to be 1. And then the bottom is going to be Vf over Vf times Vg all over Vg plus 1. Okay, so it just simplifies it a little. Maybe it's enough for you to feel like that's useful. Maybe not. Maybe you didn't want to do that step. But in this equation, I can say I know everything in this equation. Okay, they told me 40% of my volume was liquid and 60% was gas. Now, they didn't tell me of what. 50%, 60% of what, 40% of what. So I can choose whatever I want to. So I'm going to say my volume total is equal to 1 meter cubed. And so that makes the volume of my liquid to be equal to 0.4 meters cubed, and the volume of my gas to be equal to 0.6 meters cubed. I like to choose nice even 1 meter cubed. I don't have to. I could choose 29.63521 if I wanted to. I don't know why I would. But maybe thermodynamics is not enough of a challenge to me, and I want to make it more of a challenge. That's what I would do. Okay? I would choose something, but I would highly suggest do something simple. Okay, now the other thing we need, so now that gives us this, and that gives us this. We need to have the specific volumes, and they told us that this problem, they said it was at 150 degrees Celsius. So 150 degrees Celsius, now we can go to our tables. So let's go to our tables. And let's go to 150 degrees Celsius. And we're going to go to the temperature table, temperature saturation table. It's going to be the second page of the temperature saturation table. And we're going to see 150 degrees Celsius is right here. And we can read off here what our specific volumes are. 1.0905 and 0.3928. So my specific volume of my saturated liquid is 1.0905, and my specific volume of my saturated liquid is equal to 0.3928. Is that correct? The liquid is times 10 to the negative third. Absolutely. This is times 10 to the negative third. Okay? That is also going to be checked on, and if you understand that. Some of these tables have this times 10 to the negative third in the chart, and some of them don't. Remember, what they do is they take the number in the chart and they take it times 10 to the third. They take it times 1,000 and put it in the table. To get it out of the table, we have to divide by 1,000. Okay? Remember that. I will check that, make sure you know that. So now I have everything. Now I have everything in this table, everything here in this equation. So now I can go ahead and plug it in. So quality is equal to 1 all over VF, which is 0.4, divided by VG, which is 0.6. I don't have to worry about the units because they're going to cancel. Specific volume is going to be 0.3928 over 1.0905 times 10 to the minus third, and there I'm going to add 1 to that. So I'm going to get, let's do here, 0.4 divided by 0.6 times 0.3928 divided by 1.0905, 10 to the negative third. I'm going to add 1 to that, and I'm going to divide that by 1. And I get an answer here of 0.00415, or 0.415%. That's my actual quality. This is much different than when I look at the volumes. The volumes, I said it was 60% vapor. But that vapor is so very, it doesn't have as much mass as liquid water has so much mass. So even when 60% by volume of a container is vapor, the quality of it is still 0.4. We haven't even reached 1% quality, which is a little bit of a brain, it messes with your brain. Okay, so make sure that you understand the difference between quality, which is dealing with masses, and anything they give it to you by volumes. Any questions here? Okay. Going a little, sometimes with you guys I go a little faster than the 8:30. Sometimes I go a little slower. Today I'm a little bit on the fast side. Okay, let's now go to here again. I'm sorry for those of you at home. I'm sorry about clicking back and forth. They've updated this system, and so that it only records one of my screens, and I'm just not used to getting it back and forth, and I'm just not clever enough to understand how to do it or remind me. I need to have a producer for my lectures. Okay, next example, and maybe the last example that we're going to deal with. So as we get going in thermo, we're not going to just give you problems that are going to be find a property problem. We're going to give you first law problems or the other problems and ask you to use finding properties in them as a tool. Okay, so here's the first one of those things. So in this example problem, you're going to have a closed rigid tank again. With R134A, the tank has a volume of 1.5 meters cubed. Okay. Initially, the tank is at 10 degrees Celsius. It is heated until the contents is at 50 degrees Celsius and saturated vapor. Here's the question. How much vapor was present at state 1 in kilograms. Okay, I want you to think about this. I want you to see what you would do in this case. I think you should draw a picture, a TV or a PV diagram. I want you to think through what you would do here. Okay, so I'm going to give you 2 minutes, and then we're going to come together and I will tell you what I would do in this situation and how I want you to start thinking about this, because this, it does not tell you all the information directly in the problem statement. This expects you to use your understanding of the information to help guide you through where you need to be. Okay, that's 2 minutes. That's not a lot of time, but at least what I want you to do is, I want you to think about what you would do before I give you the path, because again, when you see the path that I'm going to follow, it might make sense to you. I want you to struggle with it a little bit so that maybe it can, when I show you, it locks it in a little bit more. So I'm going to tell you what I do whenever I see problems. The first thing I'm going to do is draw a picture. In this case, it's just a simple box. I'm going to draw a box here. It's going to be a rigid tank. I'm going to put it says R134A in it so I don't get confused and say that I'm dealing with water or something. And I'm going to say the volume here is equal to 1.5 meters cubed. And then I'm going to clearly set my states here. I'm going to say state 1. I'm going to put everything I know for state 1 and everything I know for state 2. I'm going to put it into a list. All right, so my temperature 1 is going to be equal to 10 degrees Celsius, and my temperature 2, my temperature 2 is going to be equal to 50 degrees Celsius. And the other information they told me at state 2 is that I'm going to be at a saturated vapor. Now I know I have to have 2 pieces of information to set my state. And so I can only set state 2 right now. I can only directly set state 2 because it says temperature 2 is equal to 50 degrees Celsius and it's a saturated vapor. Okay? It doesn't look like I have enough information to set state 1. But I do. I just have to go through what the problem is trying to tell me. Okay, I have to speak thermodynamics, the language of thermodynamics. So what I would do next is I'm going to draw, what I find often helpful is to draw a TV diagram. Okay, and so I'm going to draw my vapor dome. And I know I have 2 temperatures that I'm going to be dealing with. And so I'm going to go here and I'm going to say, well, my first temperature at 10 degrees Celsius, let's just draw this one. And then I'm going to have a 50 degrees Celsius here, and I'm going to draw another vapor dome here. Not vapor dome, saturation line here. I don't know what those pressures are. I could look them up if I wanted to. But it's a little diagram. I do know where my state 2 is. Okay, because state 2 said it's 50 degrees, and it's at a saturated vapor. And this point right here is going to be state 2, because that line coming down here, that's my saturated vapor line. I know I'm on there. I know definitely where I am for state 2. Where is state 1? I'm pausing just for you to think. Where is state 1? Maybe you know exactly where state 1 is. Maybe you don't, but I want you to think about it for a second. I will tell you where most students say state 1 is. Right here. That's 10 degrees Celsius, state 1, but we have to think about what that means. If that circle, that purple circle was state 1, that means that as I added heat and go to state 2, that's a constant pressure process, right? Because this is pressure is equal to constant. That's not what's happening here. It's not a constant pressure process. My pressure is going to change as I heat that tank up. There's nothing to relieve the pressure as that heat is going to be heating up that. So where am I? Well, the problem statement did tell me where I was, but I have to kind of read between the lines, which is all what thermo is, reading between the lines. And that's why I want to implore you to try to learn how to read between the lines yourself, because if somebody tells you how to read between the lines, it seems very simple. But until you learn that skill, you're going to be powerless on an exam. Okay. What they told me was that it's a rigid tank. So rigid tank means that the volume 1 is equal to the volume 2. That's what rigid tank means. And it said it was a closed system. So mass 1 is equal to mass 2. If the volume doesn't change and the mass doesn't change, then the ratio of volume over mass wouldn't change, so the specific volume 1 has to equal the specific volume 2. So I know actually in this case that my states have to rely on that line. They have to be on that line. And so my actual state 1 is going to be right here below it. This is state 1. And my path is going to be this direction. This is how I go from 1 to 2. Okay? Rigid tank was the key information here. Closed system was the key information here. Now I can go and solve this problem. Now I know the second piece of information for state 1. Now I can set both the states. Okay? But the first thing I want to do is find out what the specific volume is at 2. So let's find out what the specific volume is at 2. Okay? I go to my tables. I'm going to try to remember here today, for those of you at home, to get my tables back and forth. I'm going to go to my tables. I'm in R134A. Note, just a side note, one of the questions I've been getting from some people, and it's a fair question, is remember we're looking a lot in the SI tables. There's a set of tables right after this in English units. It just repeats it in English units. So you don't have to convert everything into Celsius. There is a whole bunch of tables that are in Fahrenheit. Okay, I go down here and I'm looking for 50 degrees Celsius, and oh, darn it, there's 48 and there's 52. There's not 50. But luckily 50 is halfway between 48 and 52, so I can go here and I can just do that quick interpolation between these two values. This is my saturated vapor value, 0.0159 and 0.0142, so I can just do an easy interpolation, and so that's what I'm going to do. I'm going to say V2 is equal to 0.0159 plus 0.0142 and divide that by 2, and that gives me a value of, when I type it into my calculator, 0.0159 plus 0.0142 divided by 2 is giving me 0.01505, and this units here is going to be meters cubed per kilogram. So that's my specific volume at 2. I can go up here and say my specific volume at 1 is the same value, 0.01505 meters cubed per kilogram. Okay. I still have to remember, what was my question? My question was, how much vapor by mass was there in state 1? So I'm needing to figure out what the quality is. They didn't directly say find the quality, but I need to figure out what the quality is because the quality tells me by mass how much vapor is and how much is liquid. And so I had to look at this number and see if I can find out what the quality is. Okay, so that means I'm going to use this quality equation. V1 is equal to VF plus X times VG minus VF. Okay, and I'm going to have to solve for X. All right, I know what V1 is. V1 is equal to V2, so I know what that is. I had to find my VF and my VG. So I go back to my tables, and I go to 10 degrees Celsius, and there's not a 10 degrees Celsius entry over. There's 8 and 12. So I'm going to have to interpolate twice here to find out what my VF is and what my VG is. And I have to remember this number. I have to look up and say, oh, this is one of those things that has 10 to the negative third in it. I have to work on this. But it's nice because it's halfway between that I can find out what VG and VF are. And so that is what I will do here and find those things out. So VF is going to be equal to 0.7884 plus 0.7971 divided by 2. I haven't used the 10 to the negative third because it really doesn't matter here until I get my final number. 0.7884 plus 0.7971 divided by 2. This is going to be 0.79275. Now we can say times 10 to the minus third. And my VG is equal to 0.0525 plus 0.0460 divided by 2, and that's going to give me divided by 2, 0.04925. Okay, so now I have basically made an entry for 10 degrees Celsius. And now that I have that, I can plug it into my quality equation. So I'm going to have 0.01505 is equal to 0.79275 times 10 to the minus third plus my unknown x times 0.04925 minus 0.79275 times 10 to the minus third. And so let's solve for x here. Plug it into the calculator, 0.01505 minus 79275 times 10 to the minus third divided by 0.04925 minus 0.79275, 10 to the negative third. And I get my quality x. When I do that calculation, x is equal to 0.294. And that is the right answer. But if you look at your diagram that you drew up there, state 1, that doesn't look like the quality is 0.924 at all. That looks like the quality is around 75%. But you have to remember that you made that drawing. You did not take an accurate representation of what the vapor dome looked like. Now, there is an alternative homework assignment where I ask you to map out the vapor domes for all 5 substances, water, ammonia, propane, R134A, and R22. It's a good alternative assignment to do because what you will probably notice is that the actual vapor dome looks something like this. It's very skinny and it goes way over here like that. And so if we were to draw this accurately, this is what that process looks like. And that more resembles that the quality at state 1 is 25% or 29%. Okay, so I just want you to understand that the drawings that you provide are drawings, they're sketches. They're supposed to help you, get you in the right realm, but they're not exact. And sometimes they can make you feel like you're wrong if you don't draw them perfectly. Sometimes my domes are, I just draw a dome. I don't try to make it exactly what it happens. In this case, it can draw you off. Okay, so we now know our quality is 0.294, 29.4%. Okay, how much vapor do I have at state 1? Well, the question is, how much mass is there in the tank? How much mass is there in the tank? Because I know that 29% of that mass in the tank was vapor at state 1. I have to know how much mass is completely in the tank. Well, here's what we know here. At state 2, we know it's all a saturated vapor. And so I know that the specific volume for the saturated vapor is equal to 0.01505 meters cubed per kilogram. And I know the volume of my tank is equal to, the volume of my tank was equal to 1.5 meters cubed. So I could find out what the mass is at state 2 by taking the volume at state 2 over the specific volume at state 2, which is 0.01505. Sorry, that's wrong. 1.5 meters cubed. I would have found out that issue in a second when I did my units. 0.01505 meters cubed per kilogram. And I'm going to find that that's equal to 1.5 divided by 0.01505. 99.668 kilograms. And now, if that's the total amount, I'm looking at for only 29% of that. So I take 0.294, and I find out that the mass of the vapor at state 1 is going to be equal to 29.30 kilograms. This problem is indicative of what you will be looking at this semester. Homework problems are going to look like this. They're going to give you a nice little problem statement. It looks pretty easy. Hey, I have R134A. It's at 10 degrees. It's heated up to 50 degrees. No big deal. How much mass is there? There's no equation that gives you that directly. There's a thought process that you have to go through, and you have to understand quality, and you have to understand rigid tanks, and you have to understand closed systems. You have to put all those pieces together to get your final answer. And as we practice that, by doing homework after homework after homework after example after example after example, you're going to start to gain that perspective, and you're going to start to see that in your head. But it does take some dedication. And that's where thermo starts to go into that point where it gets a little bit more demanding of your time and demanding of your attention. Okay? You can all do it. I've seen students that have been very, very successful, but it requires some time and effort. Okay, what questions do you have for me today with this material? Yes? This is not on the test. This is kind of leading us into the next stuff. What will be on the test will be, I will give you 2 properties, and you need to set the state and find a third property. That's what's on the test. This is a little bit more where we're going to be going here. It's still, make sure we're still practicing looking things up, looking values up, but this is going to be exam 2. All right, I've waited my awkward amount of time. You're free to go. Enjoy your weekend. If you have questions, let me know. But again, there's no video lecture on Monday. There will be an in-person question and answer session. Bring your questions. I'll record both the 8:30 and the 12:30 and post them up as fast as I possibly can. But until then, have a good weekend, and let's go Cats.